I just want to make sure that before you watch this lecture and subsequent lectures in this series, you actually go through the lectures on two different topics. First one is the finite volume method using an unstructured mesh, parts 1 through 4, and then also the simple algorithm on a collocated mesh where we just used basically a nice Cartesian grid structured with IJK ordering. And again, those have parts 1 through 5. If you do not watch these lectures ahead of watching this particular lecture, you will find that pretty soon you will get confused because you will not understand the equations that I'm about to present. Okay. All right. So getting that out of the way, in this lecture, even though it's a general lecture on how to use the simple algorithm for an unstructured mesh, I am actually going to use this example problem to demonstrate some of the concepts. So I just want to show you what this example problem is. So this problem here on the left that you see, this is the driven cavity problem in a square cavity. This is the one that we solved using a staggered mesh in one of my earlier videos. So basically what you have is a two-dimensional square cavity with walls all around. The top wall is moving tangentially. This is called the lid, or the cap, and it's moving at a certain speed. And once that happens, it sets up a recirculation pattern. And so you have a strongly recirculating fluid flow pattern. Okay. Now here, of course, we are going to use an unstructured mesh, and to sort of demonstrate what an unstructured mesh brings to the table, I'm actually not only going to reproduce the results for this problem using an unstructured formulation, I'm also going to solve this problem where I now have a 60-degree rhombus, again, of length scale L in both directions, and the top wall is moving. Okay. Here are some of the parameters I'm going to be using. And as you can see from the calculations, if I use a lid velocity of 0.01 meters per second versus 0.1 meters per second, I get two different Reynolds numbers. So we're still in the laminar flow regime, and that's what we are dealing with. All right, just to refresh your mind, these are the results we had obtained using a staggered mesh. So I have the link here. So we solved this particular problem. Here's what the fluid flow pattern and the pressure field looks like. You're probably already familiar with this. This is for the Reynolds number of 1000 case on an 80 by 80 mesh. And here is what the convergence plot looked like. Okay, so this is just as a reference point because we are going to do the same problem using an unstructured mesh formulation, and hopefully we get the same results and similar kind of convergence, which we are expected to. Okay, next, what I want to do is, again, this goes back to my earlier comment that you should look at the videos or watch the videos on the simple algorithm on a collocated mesh, because this algorithm here that I'm showing is straight out of that, and nothing really has changed. So this is what we had earlier, and the algorithm stays the same. Whether it's a structured mesh or an unstructured mesh, this is what you have. However, for today's talk, I am going to focus on this part of the algorithm because it won't be possible to have all the parts explained in details in one lecture. So in today's lecture, part 1, I'm going to simply talk about solution of the momentum equation. And that has 3 parts. The first part is, how do you calculate the links of the momentum equation? Okay. So we are going to go through all the equations and look at some sample coding so that you understand exactly how that is done on an unstructured mesh. And then we will also talk about the solution of the x momentum equation. The y momentum equation is going to be identical, so I'm just going to skip that. So that's where we will end today. And then in the next couple of lectures, I will talk about the other parts of the algorithm. All right. So just to go back and refresh our memory, recapitulate some of the concepts, essentially we are looking at When we talk about the momentum equations, we're talking about an advection diffusion equation where J is the total flux, and it has two components, an advective flux and a diffusive flux. Okay, so those are the two parts. U is the velocity, shown here in bold. Phi is some advected scalar, and I'll get to that in a moment. And then gamma is your diffusion coefficient. In the case of the Navier-Stokes equation, this will be your viscosity. And again, phi is some advected scalar. In this case, the advected scalar will be velocity components. Okay. So when we do finite volume integration or finite volume formulations, basically what you do is integrate each term over a volume, V naught. So the transient term becomes that. And for the time derivative, you can either use a backward Euler method or a Crank-Nicholson method or other methods. Okay, so I'm not going to get into that. And if you use, for example, the first order backward Euler method, then this is what you're going to get. Okay, so basically this is at time index n+1 minus at the same quantity at time index n divided by delta t times the volume. So that's straightforward. Then we get to the transport terms, and I have talked about this earlier, that there are two approaches to treating the transport terms. One is where you treat both in combination. For example, that's what we did in the hybrid or exponential scheme. But the more common approach is to do an operator splitting, and you treat the advection and diffusion separately, as if they are completely isolated effects. Okay, and we have already talked about this diffusion term, which is really the problematic term when it comes to unstructured grid, because this involves an extra gradient. As you see in the advection term, there is no extra gradient. It's just divergence of a flux. But here, the flux for the diffusion term, the flux involves a gradient itself, and that's what makes it complicated. In other words, it's second derivative as opposed to first derivative, which makes it complicated. And this is where you really need to watch the finite volume method for unstructured mesh and how this term is treated. So in this lecture, I'm simply going to use results of what I talked about earlier in these other lectures on the finite volume method for unstructured mesh, okay, without going into details of how those expressions are derived. The one that I will talk about here, though, is this term, because this is not something we have talked about in the other lectures, okay? And this is, as you can see, directly related to fluid flow, right? So we are going to talk about this advective term in more details. Now, the advective term, if I just take the divergence of rho u phi, of course, I can apply the divergence theorem, okay, which is sort of our main working tool when it comes to finite volume methods, right? And then this divergence can then be written as a surface integral. And I have a little picture here showing you a control volume, volume V naught, surface area S. So the volume integral becomes a surface integral. And now you have basically the flux rho u phi dotted with the surface normal summed up over the entire area. That is what that is, okay? And just again, to bring things into perspective, here are the values of phi for the three different equations: continuity, x momentum, y momentum, although this is what we are talking about right now. Okay, so if I plug in phi equal to u, then I get my x momentum equation. And I mentioned already that gamma is the same as viscosity. And then the source term on the right-hand side, you are basically going to get dp dx, the pressure gradient, and then body force if you choose to have one, okay? And similarly for the y momentum, you have dp dy and some body force in the y direction if you choose to have one. All right. Okay, so going back to our advective term, we have this, okay? And now the surface integral can be further written in terms of a summation over discrete faces, because our control volumes, since we have a mesh, the control volume is bounded by discrete planar faces, a set number of faces. So if you have a triangular cell, you will have 3 faces. If you have a quadrilateral, you will have 4 faces, etc. In 3D, if you have a hexahedron, you will get 6. If you have a tetrahedron, you'll get 4, and so on. So this is the summation over the faces. So from this point onwards, F, just to emphasize, represents a face. So this is a summation over faces. Okay, so all you have here is u dot n at the face, times the area times the density at the face, and then the advected scalar, okay, which, as I mentioned, could be either U or V. All right. Now notice that this quantity here, and this is from your basic undergraduate fluid mechanics, this is nothing but mass flux at the face, okay, in kgs per second. I call it flux, but it's actually the mass flow rate at the face, okay? And this is normal to the face because you're doing U dot N, okay? Now, one of the important things to understand is that if I have a control volume like this, okay, and this is the face that I'm looking at, this particular one, okay, this surface normal is always, by definition, when I'm applying the divergence theorem, okay, in other words, when I came up with this formula from the volume integral, by definition, this surface normal is always pointing outwards. So when you write your code and calculate your mass flux, okay, you got to make sure that the surface normal is pointing outwards from the control volume. Okay, so keep that in mind. That is something very important. We'll revisit that later on when we get to actually developing codes and so on. Okay. So essentially what I have is this advective term, essentially, which I'm calling JA. It's basically the volume integral of the advective term is nothing but mass flux times the value of the advected scalar at the face. Okay, and to compute the mass flux, we need to compute normal velocities of the face. And this, as we know from our previous discussions of the simple algorithm for collocated mesh, requires what's called the pressure-weighted interpolation method. Okay, now I'll talk about how that exact same method is to be adapted to unstructured mesh. Okay, the phase value of the advected scalar is to be approximated using any of the schemes that we have discussed earlier. For example, if you use first-order upwind, then we know that the advected scalar phi f at the face, okay, is here, basically is equal to phi naught if the U dot N, okay, is positive, and it is, if that is negative, now rho f, of course, whether you keep that or not doesn't really matter. It's a positive scalar quantity. So bottom line is, if the normal component of the velocity is positive, then you use this value for this face value. If it is negative, then you use this value for the value at the face. Okay, this is simple first order upwinding. Only thing is the difference with an unstructured mesh and difference between an unstructured mesh and a nice Cartesian grid is you are not looking at U and V components. You are actually looking at the dot product of the velocity component with the surface normal, which, if you think about it, if I have a grid which is aligned like this, okay, the U dot N at this face basically becomes the small u, and the U dot N at that face basically becomes the small v. And that's the reason we were using small u and small v earlier for a nice Cartesian mesh. But now we are using the dot product. Okay. And as before, and we have talked about this in this video, how to use these so-called switching functions rather than if checks for the upwind differencing, you end up getting this sort of an expression. So this m dot f times phi f, which is what I had here, okay, essentially boils down to this expression using this so-called switching function. Okay, in other words, you don't have to do any if checks. All right, now if you choose to use central difference instead for the advective term, which some people do, you often have these blending schemes where you blend central difference with upwind difference, okay? You choose to do that, then of course the phi f will basically be a distance-weighted interpolation where these WFs are weighting functions. And again, we have talked about these when we talked about unstructured mesh, how to calculate them. Okay, they're based on inverse distance weighted interpolation. So for a nice uniform Cartesian mesh, WF will be 1/2. So you'll have phi naught plus phi n divided by 2. That's what you'll have. Okay. Now, if you use second order, if you want to use second order upwind differencing, that gets a little bit complicated for an unstructured mesh. This is something I will discuss in a separate lecture. For now, I will skip that. Okay. So from this point onwards, we are going to use first order upwind for advection and second order central differencing for diffusion, and then we will build our equations based on that assumption. Okay. Let's also now talk about a little bit about the pressure source. Okay, so this is our momentum equation source for the x momentum, negative dp dx, but now integrated over the volume. This volume is now arbitrary in shape. So, for example, you can't write this as P east minus P naught divided by delta x, or sorry, P east minus P west divided by 2 delta x times volume would be delta x times delta y. You can't use that kind of an expression anymore. So how do we do it in general for an unstructured mesh? Okay. So this is where I'm presenting a little derivation, and this derivation is important because you can use this for other things. So imagine I define a vector q. Okay. Again, in my notations, anything with bold is a vector. Okay. Anything that's not a bold is a scalar. So this vector is a scalar pressure times some unit vector in the x direction. Okay. I'm defining Q that way. So if I calculate divergence of Q, the divergence operator looks like this, right? Or the nabla operator, ddxi plus ddyj. Divergence means I'm dotting it with this vector, which is p times I. So clearly you can see this is going to give me dp dx, okay, because the j dot I is 0. Of course, you could extend this to 3D also. I'm just showing it for 2D. So therefore, we can say that in integral of dp dx dv is the same as volume integral of divergence of q dv, provided q is defined as p times I. Okay. And now we can therefore calculate our source term. So instead of using dp dx dv, I'm using divergence of q dv, which then I can apply the divergence theorem, convert it to a surface integral from a volume integral like we have always been doing. And this now becomes q dot nda. And now I bring back my definition of q, which is p times I. And of course, I dot n is nothing but the x component of the surface normal, or nx. And so when I write this integral for a discrete number of faces, basically I get the pressure at the face, okay, times the x component of the surface normal, which comes out of this dot product at that face, times the area of the face, okay, which comes out of this. So this is my formula for calculating the source term. Okay, and it is applicable to any arbitrary control volume shape. Doesn't matter what type of mesh you're using. Okay, 2D, it'll be triangular, quadrilateral, or arbitrary polygon. In 3D, it'll be tetrahedron, prism, hexahedron, arbitrary polyhedron, doesn't matter. Okay, equally applicable. Now, one of the things you have in this formula, of course, is the pressure at the face. Okay, now pressure at the face is not something we calculate pressure at cell center. So if I have two cells, and I've just simply numbered them, the first face adjoining face F, and then the second face adjoining, or the second cell adjacent to face F. Okay, so these are the two cells on the two sides of the face, 1 and 2. Then I'm again going to use a distance-weighted interpolation to calculate the face value. So that sort of completes my total procedure for computing the source term of the x momentum. Likewise, for the y momentum, instead of nx at the face, I'm now going to use the y component of the surface normal at the face. Okay. So here are the final set of equations. Okay, and I have a picture here showing a control volume naught. So remember, the discrete equation or the finite volume equation I'm developing is for this cell. Okay, and then here is a neighboring cell, a typical neighboring cell. This L vector basically is the vector joining the two cell centers. Here is the surface normal shown. The face is denoted by F, and the star here denotes the face center. And here is a tangent that I'm also showing on the face. Okay. So putting everything together, this is what it looks like. So this is the advective term, the time derivative term. This is the advective term that we just derived. And then this is the diffusion term. Notice that here I have this tangential flux. And again, I'm not going to discuss this here. As I said, the lectures on the unstructured mesh finite volume method already talks about that, how to derive that. I'm simply going to use the result. So the m dot f we discussed already. And then here are what the tangential fluxes look like, okay, in 2D and 3D. Here in this lecture, I'll mostly talk about 2D, and I'll show you some sample codes for the 2D, okay, where this A and B with bracket F simply means vertex A off face F and vertex B off face F as shown in the figure. All right. And here are your sources. Okay, so of course, phi is u in this case, the advective scalar. And then this is we already talked about deriving this, the pressure source. And then you have a correspondingly pressure source for the y momentum equation. Okay. Now, if we write this equation in steady state, so just the transient term is easy to pull back in, but let's just talk about the steady state equation just for simplicity. This is what it looks like. Okay, so from here, we can clearly now identify and write down the different link coefficients. So if I write this equation in this generic algebraic form that we have always been doing when we talk about the simple algorithm, so A naught being the diagonal, some people call it AP. As a matter of fact, in my code, I call it AP. Okay, so AP times UP, and then summation over the faces. This is basically A neighbor times U neighbor. Okay, so the number of neighbors you have are equal to the number of faces of the control volume. So if it's a triangular control volume, you have 3 such off-diagonal elements. And then the right-hand side is your essentially the sources and whatever else. The sources could be from various physical mechanisms. Pressure sources would be one of them. So it's pretty clear to compare this equation with that equation to derive these coefficients. So here is the diagonal, okay, which is obviously a sum over all the faces. And then here is the off diagonal. And then the right-hand side is comprised of the pressure sources, which we discussed earlier, and then what I call a skew source. This is something we also discussed when we talked about the unstructured finite volume method. Basically, what happens is this term here, which is the tangential flux right there, gets popped over to the right-hand side of the equation and treated explicitly, as you can see from these star marks here, in the skew source. Okay. So those terms basically got popped over to the right-hand side, and they use vertex values, and they're calculated explicitly. So use previous iteration values for those. Okay, so this is something, again, we have talked about when we talked about unstructured mesh formulations. It's a common practice to do that. You could, of course, have an implicit formulation, but then your stencil will be very big, and you will have all sorts of issues to deal with at the boundaries. Okay, so that's the x momentum equation. And likewise, we have the y momentum equation. It's identical. As a matter of fact, these link coefficients for the x and y momentum equation are the same. Okay, so these two, the A naught and the A neighbors, the only differences are in the fact that here you will have the y pressure source, and likewise here you are using V instead of U for calculating the source terms, the skew source. Okay, but the other coefficients are the same, so you can reuse them. You don't need to calculate them twice for the x and y momentum, the A naught and the A neighbors. Okay. So I think that's as far as the material is concerned. And now what I'll do is I will show you a bit of coding so that you understand how these equations are used. And while I'm doing that, I'll keep this slide open because these are the equations we are going to finally code in. Okay, so I will begin with the main program. Okay. And the main program, you can see, so this is the outer loop iteration, okay? And if I go back again to my algorithm, so that's the outer loop, that's this red arrow, right? Within the outer loop, you see the first thing we are doing in the main program or the main algorithm is calculating the links and sources for the x and y momentum. And then we are solving the momentum equations. Now, outside of the outer loop, however, there are some things that you need to do. And that is one of the things that's important for unstructured method is you need to process the grid, prepare and store all your connectivity information. Okay, so all that we have to do, you have to set boundary conditions, and then you have to initialize everything. You have to, like it says here, guess these values. Okay, you have to allocate all these arrays. You have to set values for them before you start your algorithm, because it's an iterative algorithm, so it needs an initial guess. All right. So that's what you see here. I have a subroutine. By the way, this is a Fortran program. For those of you who use MATLAB, you should be able to follow this quite easily. So this is just a function call, which calls this thing called grid, where all the grid and boundary condition information is processed. Okay. This is where the connectivity data is constructed and stored. This is where the boundary conditions are set and so on. I will show you what's inside it. Okay, so up to this point here, and I'm not going to go over it, all the connectivity and all the area calculations, volume calculations, surface normal calculations, all of that has been done here. It's a pretty big subroutine or function, but I'm not going to go over that because that's something I've already talked about in the unstructured finite volume formulation lectures. What I'm going to show you, though, is the fact that we now also have to apply boundary conditions. Okay. Now, generally, the boundary condition is intimately tied to the grid. But here, since I'm just showing you a small sample code for a small sample problem, I have taken a shortcut and set the boundary conditions accordingly. So basically here, what I'm saying is if the face, y coordinate of the face is within a certain tolerance of the top of the cavity, okay, so you can see this length is len r is basically the length, capital L, that I had shown, times sine of theta. Now theta, if theta is 90 degrees, then it's a perfect square. If theta is 60 degrees, then it's inclined, right? So depending on what I have, but nonetheless, within a tolerance of 10 to the minus 6, if the y coordinates of the faces are within that tolerance, then I hardwire essentially the u velocity, okay, to the lid velocity. That's how I'm setting my boundary conditions. All the other faces have been by default set to 0, the velocities. So all the side walls, bottom wall, etc., they will remain zeros. Okay, only this one is overwritten based on this premise. And then I do the same thing with vertex values also, because as you may imagine, to calculate those tangential fluxes, I also need vertex values. And that's why I'm doing the same treatment. So anytime I have a node or a vertex which is on the top wall, its value is set to ulid, as you can see here. Okay, so that's where I'm setting my boundary condition. All right, then we have this subroutine called initialize. And as I said, this is where you allocate memory and you initialize all of the arrays. And I'll just show you what is being done here. So for example, I am allocating all the cell center arrays. So this is u velocity, u at the cell center, v at the cell center, pressure at the cell center. Okay, and I'm setting all of them to 0. You may not set them to 0, but I'm choosing to set them to 0. Okay, then I have face velocities. Okay, similarly, this is u at the face, v at the face, pressure at the face, and also I want to calculate and store m dot at the face. Now, one of the things I forgot to mention when I showed you the final equations is if you look at these equations, okay, to calculate the link coefficients, as you see here, I do not need individual u and v components. Okay, all I need is the mass flux normal to this face. I need to compute that and store that. Okay, this is all I need. So there is no reason for you to calculate and try to store u, v, w components separately. It's a waste in terms of memory. Not only that, later on when we talk about the pressure-weighted interpolation method, you will see that calculating those individual components is actually quite problematic. Instead, calculating the normal component is much easier. Okay, so keep that in mind, that really for an unstructured mesh, what you need is mass flux at a face. You don't need individual u, v, w components. Okay, so nonetheless, I have allocated memory for u, v components. Okay, you may or may not. And then pressure at the face, which we are going to need, of course, to calculate pressure sources, and that m dot at the face. Okay, and again, I have set these to 0 by default. Okay, and this is where I also load my boundary conditions, because I know that if I'm at a top boundary, okay, I need to have non-zero values for velocity at the face, the u velocity at the face, and that's what I'm doing here. I'm taking the boundary condition information and loading it onto the face velocity. Okay. This, by the way, as I showed you in the other subroutine, I've already set. Okay. So this has already been set to some values. It's just copied over to the generic face velocity array. Likewise, I do some things. I allocate memory for vertex values, okay, and set them initially to 0. Okay, these are all going to be updated. I also allocate memory for sources. Okay, so this is the x momentum source, y momentum source, skew sources for the x momentum, skew sources for the y momentum, and then this is your diagonal of your matrix AP. Okay, this is the off-diagonal coefficients. As you see, this is sized total number of cells times 4 because I'm going to use a quadrilateral mesh. In general, this could be a number that you have to determine on the fly. Okay. And then here I also created an array for the residual in each cell. Similarly, I have sources for the pressure correction equation that I've allocated, and then diagonal for the pressure correction equation, residual for the pressure correction, neighboring link coefficients for the pressure correction, velocity correction at cell centers. This is something we will need for the simple algorithm, also allocated here. Okay, total number, size, total number of cells. NC, by the way, is the total number of cells. And similarly, mass flux correction at the face. Okay, because as I said, you don't need to calculate U phase, V phase, W phase separately and then correct them in the overall simple algorithm. All you need to correct is the mass flux at the face, because that's what you need for execution of the algorithm. Okay, and also you need pressure correction at the faces. All right, so this is allocation of memory and initialization of all the data. All right, so here is our main subroutine. So whatever we have outside the loop is done. Then we get to this part here, calculation of the momentum links and sources. Okay, and that's right here. And you can see how compact this routine is as opposed to what you would have for a structured mesh. Okay, so what am I doing here? I want to calculate the diagonal and the off diagonal of the discrete equations for all cells. So I'm looping over all cells because my number of unknowns is the number of cells in the finite volume method. Okay, I am initializing these 3 to 0. Okay, then I'm saying, oh, okay, now loop over all faces of the cell. So each cell, depending on the cell index IC, has a number of faces. If you're using a quad mesh, this will be 4. So 1, 2, 4, I'm looping over that. Okay, this is the same as looping over east, west, north, south, okay, that we do in a structured mesh. Instead, now we have total number of faces. So from that, from the local face index 1 through 4, I get a global face index. Okay, so from the cell number and the local face index, I get a global face index using this connectivity information. Again, this is something you have to go back to the unstructured mesh finite volume lectures to understand. Okay, so I get the global face index, and then I construct this quantity called MF, which is nothing but mass flux, which is the m dot that I've already calculated, times this SN sign. Now, this SN sign is something I also talked about in the unstructured finite volume method. Basically, this surface normal, as you can see, it has an index IC and J. Okay, essentially, this tells you which way the surface normal is pointed from the point of view of the cell knot. Okay, remember, the surface normal is just stored. Okay, it may be stored this way or that way. We don't know a priori. Okay, from each cell's perspective, it may be either pointing outwards or inwards. However, as I mentioned earlier, when you are actually calculating these link coefficients, you got to make sure that the m dot f that you have in this expression uses a surface normal that is pointing outwards from the cell. And that's what this does. So this SN sign actually has a value equal to 1 if the surface normal is already pointing outwards, and it has a value of -1 if it is pointing inwards. In other words, it is going to actually flip the surface normal if it was pointing inwards, okay, to make it point outwards. So that's what this is doing. It's taking the mass flux across the cell and assigning it a proper direction, which is always outwards, okay? And then what it does is it checks to see if this particular face that I'm looping over is a boundary face or not, okay? If it is not a boundary face, in other words, if the B face is not equal to 1, it's equal to 0, which means it's an interior face, then it simply takes this formula and executes it. It's a summation over faces, as you can see, okay? So what you see here is exactly what I had in that slide, okay? You can see actually the switching function here, 1/2 of absolute value of the mass flux plus the mass flux. And then this is the diffusion term right there, okay? Likewise, the off-diagonal term has a negative of the diffusion term. And then you have the other half of this part here of the switching function, okay? So that's that. For boundary faces, we are doing something slightly different, okay? Of course, we don't have two cells now. We have a boundary phase. So there is a diffusion term contribution, okay, that you will get from basically the shear stress, the viscous terms, okay? So then we get into calculation of sources. So this is where I first calculate the face value of pressure, okay? And then once I calculate the face value of pressure, I simply execute this formula, okay? So you can clearly see here, I'm looping over all cells and then looping over the faces of each cell. And I'm simply taking the pressure at the face times the surface normal. And again, I'm making sure the surface normal is pointed outwards by multiplying with this SN sign times the area, okay? That's all there is to it. And then what we get into is skew sources. For skew sources, I am actually executing this formula, okay, right there. So I have two vertex values, difference of those two, then T dot L times mu times divided by this distance or delta, okay? And that's again what we are doing here. And this is something again that I explained in the unstructured mesh lectures, okay? So you can see here, I have a T dot L that I'm calculating right there, and then multiplying it by the difference in the vertex values, okay? And then this is the, again, making sure the surface normal is pointed in the right direction divided by delta. So that then, and then finally I'm multiplying, because my viscosity is a constant here, I'm multiplying it later instead of having it in the loop for faces to calculate the actual skew source term. So by this time, I have the pressure sources, I have the skew sources, I have all the link coefficients. Okay, so I'm ready to now solve the X momentum equation. To solve the X momentum equation in this particular example, I've used a simple point-by-point Gauss-Seidel method, which I'm sure all of you are familiar with, okay? Basically, what you do is, instead of saying A naught, phi naught plus the off-diagonal terms equal to the right-hand side, you take the off-diagonal terms, pop them over to the right-hand side, and basically each point you divide the entire right-hand side by the diagonal. So that's what is going on here. Again, I'm looping over all cells. I'm trying to figure out what is the neighboring cell to a given cell, okay? So essentially, I'm saying that if the surface normal is already pointing, now my surface normal is always pointing from cell 1 to cell 2. So I'm saying if the surface normal is already pointing outward, then the neighboring cell is cell 2, which is what I'm saying here. Whereas if the surface normal is pointing inward, which would be this case here, then the neighboring cell is actually cell 1, because I'm cell 2 then in that case, okay? So that's the logic that's being followed here. And then as you can see here, I am summing up, this is the summation of the off-diagonal terms, the neighboring coefficient times the value of the velocity, okay? And this is finally my residual. Now, one of the things I want to remind you is that when we solve the X momentum equation, we solve it in correction form because we have to use inertial damping. This is something, again, I've talked about in my other lectures on the simple algorithm, okay? So that's something to keep in mind. So here we are constructing the residual. So this is the pressure source right there, plus any source that comes out of the viscous terms at the boundary. Then you have the skew source, okay? And then I subtract out the A naught, phi naught term. And then these are the sum of the off-diagonal terms. So everything together gives me the residual. And here I'm monitoring or calculating the L2 norm of the residual just for monitoring purposes. And then finally, I say the correction is the residual divided by the diagonal times 1 plus alpha. This R in UV is nothing but your inertial damping factor alpha, okay? And then once I get the U tilde is nothing but the correction in the inner loop. I add it to my velocity. So this is basically at this point U hat. And once you add this here, right here, okay, or sorry, this is actually UK. And then once you add the U tilde, you basically end up getting U hat, which is the prediction by the momentum equation. Okay. So that's what this is doing. So solving the X momentum, as you can see, it's pretty short. And the same thing you're going to have for the Y momentum equation. So hopefully this gives you some idea of how to implement things in the case of an unstructured finite volume method for the simple algorithm. In the next lecture, I'm going to actually talk about how to use the pressure-weighted interpolation method to calculate phase velocities, because we need phase velocities to compute mass imbalance, because the mass imbalance is the source term for the pressure correction equation, which is, again, something I'm going to talk about in the next lecture. So thank you all. Look out for the next lecture.